Hello, I'm Mr. McBrien. This is TEJ3M, voltage drop. So yesterday we talked about Kirchhoff's current law and essentially discussed the concept that current flowing out of any node, any location in a circuit, has to equal the current flowing in. So for this case, I1 is equal to I2 plus I3. Today we're going to discuss some more fundamental things about circuits. Talk about what a resistor does, and I know we've talked about that before. We're going to discuss the changes in an electron as it goes through a resistor. And then we're going to revisit the idea of what a resistor does to see if maybe we have a better understanding of that. Once we do, we're going to talk about voltage drop across resistors and some practical applications of voltage drop in the form of voltage dividers. Okay, so let's start with the absolute fundamentals of circuits. So pause the movie, and I want you to form your own answer about what a resistor does. Okay, so go ahead and pause the movie and think about that. Welcome back. Okay, probably the most likely answer from a high school student would be a resistor slows down electrons, because that's drilled into us from science class. And if you answered that, fair enough. Because if we add a resistor to a series circuit, current goes down. In other words, it slows down electrons. Let's ask a different question. Let's ask this question. I'd invite you to again ask yourself the same thing. What happens to an electron when it passes through a resistor? Okay, welcome back. So I'm very interested to think about what you may have replied, talking about what happens to an electron when it passes through a resistor. You may have said it slows down. And maybe it won't surprise you to know that that's not the case. Electrons don't slow down as they go through a resistor. And to convince you of this, I'd remind you of the conga line principle, the idea that electrons march through circuits. The current is the same at any node in a series circuit. Don't forget, that's what Kirchhoff's law says. So the current is the same anywhere through there. In a series circuit, the current is the same both before and after the resistor. So if we measure the current through point 2 and the current through point 3, the current will be the same. Okay, so then what really happens to an electron when it passes through a resistor? The answer is it loses energy. So that loss in energy, we know that it's the case because resistors heat up and other devices do work. And that loss of energy results in a loss of potential difference. So a resistor lowers the energy of an electron as it passes through. And you'd ask yourself, okay, well, wait, how can we tell the energy is lower? And the answer comes in this concept of measuring voltage at given points in a circuit. So we can take out a voltmeter and we can measure the potential difference between point 4 and point 2. And of course, most of you will say, okay, well, that's really easy. That's 9 volts. If we measure the potential difference between point 4 and point 3, most of you will say, okay, well, that's easy. It's a wire. So the difference between there will be 0 volts. This is our clue to what's changing in the electron as it passes through that resistor. The electron loses 9 volts of potential in moving from point 2 before the resistor to point 3 after the resistor. And this takes us to our key concept for today. Current running through a resistor produces what we call a voltage drop. It removes energy from electrons. Now, that's all well and good and really easy to visualize if we're simply going from the full battery potential down to ground. And if we do that through one resistor, we know the voltage drop on that produced by that resistor is the complete potential of the circuit. So we might ask ourselves, okay, what if we throw two resistors in there? Well, in this kind of series circuit, we know the voltage difference between 0.2 and 0.3 is 9 volts. We already covered that. We can ask ourselves, okay, what's the voltage difference between 0.2 and 0.5? In other words, what's the voltage drop across this first 3K resistor? Well, it might not surprise us to learn that it's halfway. So can we prove this to ourselves easily? Well, we could do a measurement, but we can also do a bit of a thought experiment. We know because it's a series circuit, the current's the same through both of our equal resistors. Now, the power used up by the resistor, P equals IV, because the current is the same, the power is the same. So we can say that each resistor is using up the same potential. And so what we can do is say the combination of those two resistors gives us 9 volts. Each one contributes half, and 4.5 volts of voltage drop for each resistor. And in fact, if we take a voltmeter and put it between 0.2 and 0.5 or between 0.5 and 0.3, we'll see a voltage difference of 4.5 volts. So this is fine and interesting. We can also have more resistors in series. And again, no great surprise, the voltage drop divides between these equally as well. So in this circuit, we have 9 volts of voltage drop from here to here. We have 3 equal resistors. Well, if we want the individual voltage drop for these, it would be 9 volts divided by 3. Each one is 3 volts of voltage drop. And this isn't just a conceptual exercise, so we can go and we can build that circuit pretty easily, measure the voltage. So our 9 volt battery is here. We can measure the voltage difference between here, and of course it's 9 volts. But after our first resistor, it's 6 volts. There's 3 volts of voltage drop. No great shock. After the second one, it's 3 volts. And if we took the trouble to measure the trivial case, it would be 0 volts if we measured here. So as the current flows through each resistor, we get a voltage drop of 1/3. Now you might ask yourself, wait a sec, do the resistors have to be equal? And of course they don't. So we can also look at voltage drop across unequal resistors. In this case, we've got a 6K resistor and a 3K resistor in our series circuit. So these aren't the same. They don't use up the same amount of electron energy. Now, we could take and do a more detailed analysis. We could do things like conceptually dividing this resistor in half and then saying, okay, now we do have 3K resistors. But we're not going to dig too deep into that to save time. Instead, what we can say is that if we know the overall voltage drop, in this case 9 volts, the voltage drop contribution from the resistors is just based on the percent of the overall resistance. So this is 2/3 of the resistance, 9K. This is 1/3 of the resistance, and the voltage drop arranges itself according to that. So we can look at that from a bunch of different points of view. We know the current through the two of them is equal. We can in fact calculate the voltage drop based on Ohm's law. So if we have a current here of 1 milliamp, the 6K resistor, V equals IR, 1 milliamp times 6 kilo ohms equals 6 volts. The 3K resistor, 1 milliamp times 3 kilo ohms equals 3 volts. So we can calculate the voltage drop across a resistor if we know the resistance and the current through it. So here's an example here where we've got a series circuit with two resistors. We don't care about their resistance, one 10 ohm resistor and a 1.2 volt power supply, and we've measured the current to be 0.035 amps. Well, we know the potential difference, we know the resistance, we know the current, and we need to find the voltage drop across that single resistor. V equals IR, and we get 10 ohms times 0.035 amps, or 0.35 volts. So the voltage drop associated with this single resistor is 0.35 volts. Now, you might ask yourself, wait, can we do this without knowing the current through the circuit? And the answer is absolutely, based on that concept we talked about previously. Let's consider this circuit here with a 220 ohm resistor followed by a 780 ohm resistor. We can simply, based on the overall voltage drop, use percentages. R1 is 22% of the 1000 ohm resistance. R2 is 78% of the resistance. The overall voltage drop is 24 volts. R1 is 22% of the voltage drop. R2 is 78% of the voltage drop. And we can simply multiply that out and get the answer. What about, let's see, 5.08. 5.28 volts for the first resistor, which would give us 18.2 volts of voltage drop for the second resistor. I'll look forward to seeing comments in YouTube if I've got that wrong. Okay. So we can go through a different example though, and I'll actually use a calculator for that. So we can ask ourselves, okay, what's the voltage drop across the three resistors when we have a 12 volt power supply connected to this circuit? Our givens, the system voltage and the resistances for the three resistors. So our unknown is the three voltage drops. And I gave one example. So here's our equation for the first time, which is just percent of the overall times the system voltage. And multiplying that out, we get the voltage drop across the first resistor is 6.9 volts, the second resistor is 3.4 volts, and the third resistor is 1.7 volts. Okay, so there's voltage drop in a nutshell. But what about practical applications of this? If there aren't any practical applications, why talk about it in an engineering course? And in fact, there are some practical applications. Let's ask ourselves if we had a device with a 9 volt power supply, but a sensor that burns out if we have more than 2.3 volts. What do? Do we go out and add the mass and expense to our device to have a 2.3 volt power supply as well? Well, the answer is we can use voltage drop to get the voltage we need for this thing. So the concept of a voltage divider is that we carefully position resistors and pull off any voltage that we need from our circuit. And we do it by building a circuit that looks like this. Essentially, we have our big power supply here, two resistors in series, but we pull our device voltage from between the two resistors. So this effectively divides our voltage. And essentially, if you notice, this expression for the voltage we can get out of our system is really just our expression for percent of the voltage taken up. So our output voltage will be proportional to our input voltage, or system voltage, times R2 divided by R1 plus R2. And we can go through an example of this pretty simply. Here's our voltage divider circuit here. What's the voltage at V out? Well, we're given our system voltage and our two resistances. We're asked to find V out. V out is V1 times R2 divided by the sum of R1 plus R2. By my count, it should be about 1/3 of the overall voltage, and in fact it is 4 volts. So we can essentially get any voltage between 0 volts and our power supply maximum voltage using a voltage divider. And the only catch here is we want to make sure it's a low current device for reasons we won't get into. Okay, let's move on and talk about parallel circuits. We've only talked about series circuits here. We haven't talked about parallel circuits. So here's another pause point for your video. Ask yourself right now, what's the voltage drop through each of these three resistors? So pause the video and come up with your own answer, and then return back when you've done so. Okay, welcome back. In fact, this is a trick question, a good one for you to remember before we get to a test in this course. The answer is it's 9 volts for any of these three. Now why? I think probably you already get this, but I'll make sure. Notice that nodes 2, 3, and 4 are connected by wires. Anything connected by a wire has the same potential. And nodes 7, 6, and 5 are all connected by wire to ground. And so by definition, if we were to measure the potential difference from here to here, all of them would be 9 volts. So this is a fundamental aspect of voltage drop. Any resistors in parallel, their voltage drop will be identical. All right, maybe that's enough for today. So our key points: as electrons flow through resistors, they lose energy. We can observe this loss in energy based on the voltage drop of those electrons as they pass through. We can calculate the voltage drop in various ways, including simply using Ohm's law, V equals IR. But the voltage drop for a given resistor is the percent of the overall resistance times the overall voltage drop. And in low current applications, we can apply this principle to adjust a potential from a big power supply to a low voltage device using what's called a voltage divider. Okay, for your homework then, please go ahead and do the circuits activity around voltage drop. Also practice some of the calculations on the worksheet. And if you are feeling like you would like to do some more reading, there's additional links here around some very interesting explanations of voltage drop in more detail. Thanks very much. Have a great night.